So, like it or not, intuitive or not, those are the rules of the games. The universe is invariant under Lorentz transformations and not under Galilean transformations. If we're going to do physics, we're going to have to understand how to do physics in a way that is Lorentz invariant. So, one of the important things that we had discussed is our conservation laws. And we run into trouble with our conservation laws in the sense that the Newtonian conservation laws are not invariant under Lorentz transformations. What does that mean? That means that if you write momentum equal to mv, I can put little vectors there if you want to be fancy, and energy, kinetic energy for the moment, equal a half mv squared, those are not in Lorentz invariant quantities in the following sense. Of course, the momentum of a given particle is different as observed by different observers because its velocity is different. That was true in Galilean relativity as well. But in Galilean relativity, you can show very directly that if momentum is conserved in some process in one frame, then momentum is conserved for any other observer moving at a constant velocity relative to the first observer who declared momentum to be conserved. And likewise energy. It's not trivial, but it's true. On the other hand, when you use Lorentz transformations, you can find that one observer would claim momentum to be conserved and the other that it isn't. That's impossible. Momentum conservation, thus, cannot be a law of nature. Laws of nature have to be true as measured by any observer. On the other hand, Newtonian conservation laws worked well for objects that were moving slowly relative to the speed of light. Then you can, of course, pick frames to observe them in such that none of the objects move relative to you at close to the speed of light. Newtonian physics has to work. So we need and expect to find conservation laws that are extensions or modifications of the conservation of energy and momentum, but that are valid in a Lorentz invariant way. And in fact, we do. The two quantities we find that extend it are a momentum and energy, or three components of momentum if you want. And the relativistic covariant momentum is mv divided by the square root of 1 minus v squared over c squared. And the energy is mc squared divided by the square root of 1 minus v squared over c squared. Now, these are the objects. Of course, again, it is not true that momentum as measured by each observer will be the same. But what is true is if these quantities are conserved, momentum and energy, for one Lorentz observer, then they are conserved for any Lorentz observer. And therefore, the conservation of these is consistent with Lorentz invariance, and it is in fact the conservation law that obtains in nature. Now, we expect to recover Newtonian conservation laws when objects are not moving much faster, at speeds comparable to the speed of light, when they're moving much slower. And indeed, it's not too difficult to see that when v squared is much less than c squared, in the case of momentum, we drop this factor, and momentum at velocities much smaller than the speed of light is mv, and then we can use our Newton's approximation to write, remember the denominator here is 1 minus v squared over c squared to the power minus 1/2, which is approximately 1 plus v squared times a half divided by c squared. The minus signs canceled. And so there is the first relativistic correction to the Newtonian momentum conservation. At velocities much smaller than the speed of light, Newtonian momentum will be conserved. At higher velocities, you have to consider this factor. And remember, this approximation is valid when v squared over c squared is small. At velocities higher yet, you have to use this complete relativistic expression. Very nice. So we have the understanding of relativistic momentum. Notice that what this means is that as you accelerate a particle to speeds closer and closer to the speed of light, its momentum actually becomes closer and closer to infinity. It takes an infinite amount of momentum as you try to accelerate something to the speed of light. This is reasonable. It means that if you go around giving something a kick, and each kick you give it adds a certain quantity of momentum, you could ask, well, why don't I keep kicking it until it's moving faster than the speed of light? The answer is that if each kick adds a certain amount of momentum, that will only make its velocity asymptotically, as the number of kicks grows without bound, become closer and closer to the speed of light, but never accelerated past the speed of light. This is sometimes stated as saying that you rewrite this as something times v and interpret the something as some kind of relativistic mass. I don't like that point of view, and most physicists do not. We will not treat this as a change in the mass. We just treat it as the correct relativistic definition of momentum, so that the mass for us is going to be the object that's over there, and we'll see in a minute how we interpret it, and it's a property of the particle. So extracting the Newtonian limit of momentum conservation is a simple matter of setting v squared over c squared less than 1. In the case of energy, this is a lot less obvious. What is this? When I drop the v squared over c squared, I get mc squared. That doesn't look at all like the kinetic energy of anything. We were supposed to recover the kinetic energy conservation law. But if we follow through the Newton's approximation to the next term, things get a little better. We get the same half v squared over c squared. And that ends up being, well, expanding this, the first term is mc squared. And the second term, holy moly, a half mv squared. And of course, this is valid for v squared much less than c squared. For higher velocities, you have to use all of this. But when you think about it this way, you see the kinetic energy here, and then this famous E equals mc squared. The conservation law, if mass is conserved, then this is just a constant. As long as the particle exists, this is just a constant. And remember, shifting energy by a constant makes no difference. But the fact that in relativistic dynamics, it is possible, because of the modified momentum conservation, in fact, for mass to change. The total mass of particles coming into a process need not be the total mass of the particles coming out of a collision. This, in fact, was not possible in Newtonian physics. You'll show it in the homework. But it is possible in relativistic physics in a way that conserves both energy and momentum. If the mass changes, then we see here the rate of conversion of mass to energy. If the particle of mass m disappears and its mass is converted to energy, then this is the energy, and here is the kinetic energy contribution at slow velocities, and at higher velocities, this is the more accurate description. So we have our relativistic conservation laws. A few remarks about this. One is that if you compute, just from the expressions I wrote, E squared minus P squared C squared, you get m squared c to the fourth. This is the reason why, what is the mass of a particle? No matter what momentum you give it, the mass of a particle characterizes this property. To give it some momentum, you will have to give it some energy, and E squared can always be written as P squared C squared plus M squared C to the fourth. And this combination of E and P is a property of the particle. We call it the invariant mass, and that is what I will use to define the mass. This is a property of the particle and not of its motion. Good. So a particle has a mass as long as it exists. The other thing to note is I will not prove it, but I said, of course, different observers will measure different momenta. Different observers will measure different energies for the same system. But in fact, these four quantities, E and then C squared times P, transform under Lorentz transformations in exactly the same way that T and X do. In other words, momentum along the direction of motion and energy get mixed in the same way precisely that T and X do. So you can compute E prime and P prime in terms of E and P using the Lorentz transformations. And in particular, if the change in energy and momentum is zero in one frame, it's zero in any other frame, because the Lorentz transformation takes x equals t equals 0 to x prime equals t prime equals 0. This is why energy and momentum conservation is consistent if you use this definition of energy. Okay, now, an important canard. This E equals mc squared is sometimes invoked as the reason why nuclear processes release so much energy. Oh, because they convert mass to energy, and c squared is such a large number. That's a canard. In fact, these conservation laws, relativity was always true even before we discovered it. If Lavoisier in 1777, when he made his groundbreaking measurement that said that if you weigh the gas products of combustion and the ashes, you recover the weight of the wood that you started burning, had he measured very precisely, he would have discovered this is not true. Why? Because the wood in burning lost some heat. The heat radiated away. That means that the total energy of the system has been reduced. Converting by dividing by c squared, he would have found a very small reduction in mass. The point is that when wood burns, it doesn't produce that much energy. And therefore, it loses very little of its mass because you are harnessing weak electromagnetic forces at atomic radii. If you, on the other hand, manage to harness the strong force or forces at nuclear distances, the loss of the energy released is much larger. The change in the mass is actually measurable, and this is why the mass of 4 protons is larger than the mass of an alpha particle by a measurable amount. And but this has the statement that the sun is fueled by the conversion of mass to energy is a canard, in the same way that the statement that my fireplace warms me up by converting mass to energy is a canard. The statement that is true is that the sun produces energy by harnessing the very strong nuclear force. The other thing is that the decay of a particle not conserving mass is consistent, and it happens. We know of neutrons decaying to protons, electrons, and neutrini. The sum of the masses of the constituents is less than the mass of the neutron, which is why they come off with some kinetic energy because of the conservation of total energy mass. And all our other conserved quantities, electric charge, lepton number, and so on, are actually invariant. They are numbers, they are identical. The electric charge in a given region, as measured by different observers, is the same. So conservation of electric charge and lepton number and so on works very well. We don't have a problem. We have our conservation laws. Now let's write down the laws of physics. As I said, electromagnetism is taken care of, so to speak. It's taken care of. Electromagnetism, Maxwell's equations, were Lorentz invariants. That's where we all started from. What about the nuclear interactions? Well, we know a way of writing the nuclear interactions in Lorentz invariant form, though that was not the way they were initially written. In fact, our study of the nuclear interactions and of electromagnetism is often inherently quantum, and by the 1940s, and for nuclear field interactions by the 1970s, a relativistic version, Lorentz invariant version of quantum mechanics called quantum field theory had been developed. And we have a quantum relativistic version of electromagnetism, the strong nuclear force, the weak nuclear force. Physics is very nicely consistent with relativity, which leaves the question of gravity. We'll turn, and this is the question with which Einstein was stuck, Newtonian gravity, our poster child for a theory of physics, the first one to be really understood, the first fundamental force to be properly understood. The one that was our poster child for Galilean invariance is not invariant, as we will see under Lorentz transformations. It's not consistent with relativity. Einstein understood this in 1905 when he figured out the special theory of relativity. And it took a whole decade of Einstein to figure out the generalization. So we're going to spend some time trying to understand what's wrong, why gravity is not consistent with relativity, and how Einstein figured out how to resolve it. As for the quantum version of relativistically invariant gravity, that'll be left for your homework.